Okay. Can you all hear me?
Yes, sir.
Yeah.
Yes.
Yeah. Sorry for the delay. There was some problem with the internet. Okay. Doesn't recur. So I'm not yet sharing the screen. Just give me a second. Are you able to see my screen fully?
Yes, sir.
Yeah. Okay. So let's begin. Okay. So we have looked at how quasars are discovered, and we have realized that only a very small fraction of the known quasars seem to be having detectable radio emission. 90% of them or even more are faint in the radio or non-detectable in the radio. So for a long time, after these two populations, the radio quiet and the radio loud quasar populations were discovered, people started debating whether they were fundamentally different in terms of their physical properties, or this was just a continuum. Okay, or was this some kind of sample selection effect wherein you were selecting radio loud quasars with one technique and radio quiet quasars with another technique. And this whole issue was debated endlessly in many papers between about 1980 and 2010. There was eventually some sort of agreement of how you should define radio loud. So some people believe that radio loud should be defined in terms of the 1.4 gigahertz rest frame luminosity. If it is greater than 10 raised to 25 watts per hertz, then you call the quasar as radio loud. Or if the ratio of radio to optical flux is greater than 1, you call it a radio loud quasar. Now, at what wavelength do you measure this? By convention, you measure the radio luminosity or the radio flux at a frequency of 1.4 gigahertz, and you measure the optical luminosity or flux in the B band, right? Now, with either of these two definitions, that didn't matter too much which definition you used. There was quite a lot of disagreement whether there was a bimodality in the distribution of either radio luminosity or the radio to optical luminosity ratio. Now, for a long time, people were saying that this could be a selection effect, and the debate got somehow clarified by this paper by Ivechik et al. In 2007 on the quasar radio bimodality. So what they've done is that they have plotted the on the x-axis, they have the I-band SDSS apparent magnitude, and on the y-axis, they have a funny quantity which they call the radio magnitude, which is really strange. Nobody uses magnitudes in the radio, but they converted the radio magnitudes, sorry, the radio fluxes using the AB scale to an AB magnitude in the radio. Okay. But the thing to remember is the fainter objects in the optical are towards the right, and fainter objects in the radio are towards the bottom of the image because they have a higher value of the magnitude, right? Now, what is shown by these sort of diagonal lines over here are different values of the radio to optical luminosity ratio. Okay, remember these are both log scales. Okay, so the ratio is actually the logarithm is what is usually plotted, the log of the radio to optical luminosity ratio. So if it's 1 means they're equal, sorry, when it is 0, it means they're equal. and 1 is, and so on. So the radio to optical luminosity ratio increases as you go towards the top right. Now, so what they then did was they said, okay, we are not going to select quasars in the radio. We are just going to take all the SDSS quasars, which are optically selected, and we are going to plot them on this diagram by measuring their radio flux using a radio survey known as the first survey. So these are the first survey, right? Quantities, and which are shown on the y-axis. Now, beyond, so then what you do is that what the kind of bias that you will encounter over here is that if you had started with a radio survey, then you would have picked up objects with a high radio flux. Okay, so you would have picked up objects near the top. Okay, and so if you, let's say you picked up all with a radio magnitude brighter than 11, let's say, right? You'll find that most of those objects are lying in this region, right? And what is the kind of radio to optical luminosity ratio they're having? It is between, say, 3 and 4, these objects, right? Or maybe even between 4 and 5. You find hardly any objects with a low value of the radio to optical luminosity ratio, correct? Now, so therefore, if you selected quasars only from with starting with a radio survey, you'll only find these quasars, right? But on the other hand, if you started finding quasars with an optical survey, you'll find all of these quasars, right? And they are invariably radio quiet, right? They're not on this side of the line. They are on this side of Ri equal to 1 line, and therefore they are radio quiet. So you would think that yes, there seems to be one population here and one population here, which is very different in their properties. But now when you plot all the quasars known and their radio and optical fluxes on this diagram, you see that there isn't that much of a difference. Okay, there is a continuum. You are picking up, there is a distribution, and we are picking up in our selection process, we are picking up quasars from two ends of the distribution. And then we are saying they're very different, they're very different. Obviously, they're very different because they're part of the same population, but you are picking up the highest and the lowest in terms of the radio and to optical luminosity ratio. So what this told us, I mean, this paper, is that sometimes when you work with small samples, right? Typically in the old days, people used to work with quasar samples of 30 objects, 50 objects, 100 objects, like that. Okay, and when they did that, they naturally found they were looking at the elephant from opposite ends, and they were finding different properties of the radio loud and the radio quiet quasar population, but they were not real physical differences. But are there any physical differences at all between the radio loud and radio quiet quasar populations? There are, but they're relatively small. It turns out from this, again from the same paper, is that the radio loud quasars have a redder median color by about 0.1 magnitudes and show a 3 times larger fraction of objects with extremely red colors. So they are red, okay, and somewhat redder than the radio quiet quasars. And this is true even if you account for the K correction. Remember, generally the radio quiet quasars are found at a lower median redshift, and the radio loud quasars can be found at very high redshifts, primarily because the sensitivity of the radio surveys is such that there is a very strong Malmquist bias. Do you guys know what the Malmquist bias is?
No, sir.
Okay. So when you look at the night sky, for example, right? If you look at the brightest objects, the most luminous objects that you see in the night sky, right? Will they be close by or will they be far away? Not the highest flux, but the most luminous objects that you can detect. Remember, luminous objects are rare. We looked at that. So you don't find very luminous objects nearby. You don't find quasars in our local group, right? So the most luminous stars that you see in the night sky, right? Not the highest flux, most luminous, are the most distant on an average. Why don't you see less luminous distant stars? It's a simple answer. They're too faint. So whenever you have any kind of flux limited observation, you will have a very strong bias towards finding only the most luminous objects at the largest distances or at the highest redshifts. So radio loud quasars are very, very luminous in the radio and therefore can be detected, at least in the radio, literally to the edge of the universe, to the highest redshifts that you can imagine, right? Whereas radio quiet quasars are not radioluminous, and therefore in any flux limited survey, they will not be present at high redshifts because the sensitivity of your flux limited radio survey is insufficient for you to detect them at redshift 3 or 4. So at redshift 3, 4, all the quasars that you detect will be radio loud, okay? If you start with a radio selected sample. Of course, if you start with an optically selected sample, you can, of course, find lots of quasars at very high redshifts, as have been found with the SDSS. Okay. So because of the strong Malmquist bias, this is referred to as the Malmquist bias, that you can only detect in a flux limited survey the most luminous objects at the highest redshift. And this statement is true for any band, etc. So you don't find, because of the Malmquist bias, you don't find in any radio selected survey, you don't find radio quiet quasars at high redshift. You will find them only at low redshift. So because of these biases, there are all kinds of misleading scientific results that get published, and because they get published and other people sort of find the same results because of them having the same selection bias, you have a big school of people who believe that there is a quasar radio bimodality, and a big school of people who believe there isn't, and that can only be resolved with very large area simultaneous unbiased surveys in both radio and optical bands. Okay, so now let us ask the question, fine, we know that quasars exist, they're very luminous, they're found at all redshifts, they're luminous in all bands, but do they evolve? Okay, is the number density of quasars changing as a function of redshift? So what is shown in this figure on the y-axis is in all of the panels is the number 5, which is the number of the luminosity function. mg indicates what is the absolute magnitude in the G band of the relevant quasar, right? And what are the units per megaparsec cube? As I said the last time, this is always co-moving megaparsec cube, and per unit magnitude. So per unit magnitude interval. So this is not the integrated quasar luminosity function. This is the differential quasar luminosity function, which is plotted here. In each panel, you see a number, and that number indicates the sort of mean or median redshift of the quasars that are plotted here. They're plotted in different redshift bins. This is the center of the redshift bin. And these are various models of the quasar luminosity function. We won't go into that, but just observe what is happening to the data points, right? So in each magnitude bin, absolute magnitude bin, you find the number of quasars and you plot them. So this is at the lowest redshift of 0.54, going on to the highest redshift of 1.95. So from about 0.5 to 2, there seems to be a systematic change. So, so what is happening to the quasar luminosity function? What kind of changes do you see in these 6 panels? 1, 2, 3, 4, 5, 6. The curve seems to be shifting, right? Which direction is it shifting?
Towards right.
Yes, it is shifting towards the right. Okay, and what does that indicate? So if you forget the intermediate ones, just compare 0.5 with 2. What has happened?
It is becoming more brighter.
Yes. So what is essentially happening is that at any given absolute magnitude, the number of quasars that are there is higher at the brighter end of the quasar luminosity function, right? So this indicates that there is evolution in numbers, which means that the number of, so a number of quasars which are quiescent now were actually turned on in the past, and therefore they were at the luminosity function was to the right. Okay. Now, you will also notice that the luminosity function is measured up to different absolute magnitudes. Okay. So, for example, if I take 0.5 redshift, this is measured up to about, say, -21, correct? Whereas at redshift redshift of 2, it is measured only up to minus, say, 23 or 23.5. Why is that? Why have they not put data points on this side?
Sir, because at higher redshift, it is difficult to measure low brightness.
Yes, correct. So the low optical luminosity quasars will not get into the sample because there'll be a flux limit, right? So if you can easily detect a quasar at, let's say, -22 when it is at redshift 0.5, but if you take the same quasar and put it at redshift 2, it will drop out of your sample because it's too faint. So that is why ideally you would want to extend this luminosity function, because you can then also check whether things are moving to the right or are they moving up and down, because that also is a possibility, right? So have you, when you studied luminosity functions, have you studied density evolution or number density evolution and pure luminosity evolution? So let me explain. So by pure luminosity evolution, one means that if an object is a quasar at redshift 0, it will be a same object will be a quasar at redshift 1, and it will also be a quasar at redshift 2, right? So once a quasar, forever a quasar, right? So then, and no new quasars can form. So it's like, if you have been categorized as a quasar, you are a quasar for all time, right? Your luminosity can evolve. You can turn from bright quasar to faint quasar or vice versa, but your characteristic cannot change. Now, So that is called pure luminosity evolution. Pure density evolution means that your luminosity doesn't change, okay, but whether you are quasar or not quasar can shift. Okay, so you can turn off and turn on. Now in practice for quasars, as for most other objects, the reality is between these two extremes. There isn't pure luminosity evolution. There isn't pure density evolution. There are cases where the quasar, which is quite bright, turns off, completely off. So it disappears from the quasar population. Maybe our Milky Way may be an example. It certainly does not qualify as a quasar. It doesn't even qualify as a AGN at the moment. But maybe at some point in the past, it was like that. Like an AGN may be unlikely to be a quasar, because we remember quasars are found generally in elliptical galaxies, in bulge-dominated spheroids. It is not found in spiral galaxies. So it couldn't have been a quasar, but it could have been a Seyfert galaxy, as we shall see in a moment. So that is where the characteristic of the quasar changes drastically, right, from on to off. But there can also be luminosity evolution, which means that there is a bright quasar, but which was bright at redshift 2. Now the same quasar, if you follow it in time, will become fainter, right? Maybe 10 times fainter or 100 times fainter. It's still a quasar, but it's much fainter now. So it has moved in luminosity, right? So it moved left to right. So we don't know which of these operates, but we have reason to believe from theoretical models and observations that both of these operate. Both possibilities exist. A quasar can change its brightness over time, or it can go from on state to off state, and it can go again from off state to on state. Okay. Now we look at a couple of subcategories of quasars. We are coming towards the end of the discussion on quasars. So I'm just covering a few smaller topics now. So there are objects which are called optically violently variable objects, OVVs for short. And these are characterized by very strong and rapid variability of its optical radiation on time scales of days. So you don't even have to take a spectrum. You just take an optical image of the quasar, let's say in the V band, and you keep taking lots of optical images every day, every hour, and then you'll see that the flux changes quite rapidly. They seem to have more polarized optical emission of a few percent. Normal quasars have polarization below 1%, which makes them extremely difficult to detect. The flux is variable at other bands too, with shorter time scales and higher amplitudes at X-ray and gamma ray bands. There are other class of objects which are called BLLack objects. BLLack stands for BLLackerte. Lacerta is a constellation in the sky. BL was the label given to a star in Lacerta. Of course, it's not a star, but it's a special kind of quasar. It is the prototypical object of the BLLack class. It shows strong variability, just like OVVs. It's polarized, just like OVVs. Usually, it does not show any emission or absorption lines, unlike OVVs. OVVs do show the emission lines that you would expect, and absorption lines coming from the intermediate absorbers. But these objects, when their flux falls and their flux becomes low, emission lines begin to stand out. And then they begin to look more like an OVV. So clearly these two objects, BLLack and OVVs, seem to be somehow related. They may be part of a continuum of objects. So they are collectively called blazars. Okay. Blazars means it's a combination word of BLLack and quasar. And of course, OVV is also part of the blazar category. So together, OVVs and BLLack objects are referred to as blazars. We will revisit blazars later on when we talk about jets and how relativistic beaming can enhance the flux that you see coming from certain kinds of quasars. So now we know is that the flux variability of, or the high flux radio flux of blazars incidentally are also always radio loud, right? And the high radioluminosity of blazars is caused by relativistic beaming effects from the relativistic beaming of the jet of the quasar. And the jet of the quasar, if it is pointed towards you and the particles in the jet are moving at relativistic speeds, then there can be a very, very high flux enhancement. And if this, of course, is very, very sensitive to the viewing angle, if the viewing angle of the jet, if the jet changes direction by even, let's say, 0.05 degrees, then the flux can fall or rise quite drastically. And that is what phenomena we are seeing in blazars. When we talk about the jet phenomenon and the physics of jets, I will come back to this topic and I'll talk a little more about two ideas. One is this idea of relativistic beaming leading to flux enhancement and variability, and also relativistic beaming effects leading to the observed apparent superluminal motion. So it looks as if objects are moving faster than the speed of light. They're not, of course, but this is just an apparent viewing effect. Okay, so the light curve of one of the blazars, 3C279, is shown in this plot. Okay, on top you have observations from EGRET, which is a gamma ray telescope, and on the bottom panel you have observations from RXTE, which is a X-ray telescope. And as you can see that the change in flux seems to be more or less correlated, right? It is not exactly correlated, but when it sort of begins to brighten over here quite strongly, it also begins to brighten over here at the X-ray bands. Now, you can see here that the flux is changing on the time scales of a day, right? So it was here at 15 and it has become 20 in about a day, right? Or maybe 2 days. So the fact that the flux can change significantly within a day tells us something about where it is originating from. Okay, so where must it be originating from? Must it be originating from a region which is very small? If they're related to each other, remember the fact that the fluxes are changing in sync tells us that it's the same physical phenomenon that's happening. It's not as if something is happening at one end of the galaxy and something else is happening at the other end of the galaxy. The fact that if they're unrelated, okay, if they're causally not correlated, right, that can happen, of course, but that's very rare. It's very unlikely that things are happening in a causally unrelated way at the same time, right? So one assumes that these are causally related, and therefore they must be happening in a region that is connected in the sense of light travel time, right? So if things are changing on timescales of a day, both in the X-ray and in the gamma ray. Both the X-ray and the gamma ray emission must be happening on length scales of a light day in distance, right? So the only thing that we know in the quasar phenomenon, which is light day in size. So light day is roughly, very roughly, the size of the solar system, right? 24 hours is what you take light for travel from one end of the solar system to the other, right? So the only thing that we know that is of solar system size is the central black hole and the associated accretion disk around it. Okay, and that, so very, very clearly this phenomenon is happening very not over the entire accretion disk, but over a small part of the accretion disk. Now we are observing this change in the X-ray and gamma rays. So would this be from the inner part of the accretion disk or the outer part?
Sir, most probably from the inner part of
Yes.
the accretion.
Why?
Sir, because at the inner parts, the velocities are also higher, so it will be easy if there is some change in some part, and region is also small as compared to the outer part.
Correct, that's small, but also look at the wavelength of the emission. Okay, these are very high energy photons that are coming out. If they are thermal in nature, they must come out from the hottest part of the accretion disk. And which is the hottest part of the accretion disk, inner part or outer part?
Inner part.
Inner part, correct. So that this is coming from very close to the event horizon. Okay, just outside.
Sir,
Right. Yeah.
sir, I didn't understand the argument of the size from which this emission is coming. So when we say one light day, so are we saying that this X-ray and gamma ray flux, the increase in flux, came from different parts of the AGN and not the same, and it's not the same source?
No, what, it's very likely the same source. So let us say that something happens, right? There is, let's take a very trivial example. Suppose there is a star that, this won't happen to a blazar because the star will be tidally decimated before it reaches there. But suppose you take a black hole like our Milky Way, and let us say a star comes too close, right? You know that the nearest stable orbit of a Schwarzschild black hole is 3 times the Schwarzschild radius. So if something comes inside that, it is not going to be stable. It's going to fall into the black hole eventually. Now, that star, if it comes too close, it will also get tidally disrupted. Okay, because of tidal forces, it won't remain like a star. That gas will get just pulled apart. So that is called as a tidal disruption event. Now, so that is like, think of it as a sudden, and so when the star falls into the black hole, there's going to be a flare from the black hole. It's going to brighten up suddenly, right? Now, suppose it emits a lot of gamma rays and X-rays when that happens, right? Now, suppose that there is some other gas cloud which is nearby or something else, which gets excited by the photons that are X-ray and gamma ray photons that are emitted from this cloud. What will happen? They'll brighten, right? And they'll also maybe emit these secondary gamma rays or X-rays and so on. So if you have an explosive event in one place and a day later you have an explosive event in some other place, right? What does that indicate about the separation between these two objects? They must be separated. These two regions must be separated by very short light travel time. They can't be 5 light days away from each other, because then if one brightens, the other will take at least 5 days to brighten, right? But if they're brightening within hours of each other, they must be within light hours of each other, physical distance. This is what we are seeing, right? Now, the fact that it's correlated So there are two phenomena to observe here. One phenomena to observe is that the light changes, the flux changes by 20-30% within a day. That's one. The second is that it changes similarly in gamma ray and X-ray in two different bands. So it's very, very easy to understand if you think of a sort of spherically symmetric thing, right? So suppose you see an explosion, or let's say a supernova explodes. And let us say 3 days later, you see some X-ray emission. 5 days later, you see some ultraviolet emission. 1 month later, you see some radio emission. So you can say things about the minimum, the maximum separation between the supernova event and the radio emission. So if you say radio emission after a month, that radio must be within 1 light month of the supernova.
Right.
Right. It cannot be farther away. If it is 2 light months away, it will take at least 2 months for it to brighten up. So there are delays here also. So one can even estimate the size of the region and estimate whether there is a statistical difference between the gamma ray emitting region and the X-ray emitting region. Are they at the exact same spot, or are they slightly separate from each other? All of this can be done with this kind of analysis.
Okay, so when you're saying you have time scales of day, you mean the separation between like the difference of the peak between X-ray and gamma ray?
No, not necessarily. What I'm saying is there are 2 things. One is, see, the flux was 6 on one day, and a day later it became 10, and a day later it became 6 again.
Yes.
So there has been a 50% increase from 6 to 10 within a day, and then 40% fall within a day.
So this could be one event itself, right?
This could be one event itself.
Now
the peak, if you see the peak of the gamma ray, that seems to be slightly offset from the peak of the X-rays.
Right.
So,
Yeah.
so that offset is also small. That is of the order of light days. But
Yes.
if you just look at one panel, even if you look at one panel, you can, the fact that things are changing on light day time scales, indicate that the emission region is very, very small. It can't be galaxy sized. It cannot be that this brightening is from one end of the accretion disk and or one end of the galaxy, and something else is happening simultaneously at the other end. The probability of that happening is very, very small.
So, but we focus on the gamma ray curve.
Yes.
It suggests that this is just one event with a time scale of about 2 days.
Yes, that is correct. That is right.
Okay.
Okay, that is absolutely right. So this, I would consider this as a single event, a brightening and a fading, right? And so see, remember, if you want to say that, no, this is not happening on time scale of 1 day, but it is happening on a time scale of 10 days. Therefore, this region must be 10 light days in diameter. I have no problem. Okay, because remember, 1 parsec is 4.3 light years, right? So a year is 365 days. So it is more than 1,000 days. So 1 light day, 2 light days, 4 light days, 10 light days is still a very, very small fraction of a parsec.
Right.
Right. Okay. So far we have talked about quasar emission, but we have kept on saying that the quasar is a point source, the quasar is a point source, and so on. That is true in most of the bands, but it is certainly not true in the radio bands. In the radio bands, if it's a radio loud quasar, it will often show structures like this. So this is a VLA image in the 6 centimeter band of one of the quasars, 3C334. Okay, this is the 3rd Cambridge catalog, object number 334. And here you can see that they have lots and lots of extended structure. When we talk of radio galaxies, we will go into detail about all these things, what they mean and what they're called. But this central object is your quasar. In your optical, you will just see a point source just like this one. If you go and look at it in the X-ray, you may or may not see it, but let's say it's bright in X-ray also, you will detect a point source over here. For very high redshift quasars, you may actually detect extended X-ray emission from the lobes. Okay, any idea why? Only at high redshift. Okay, you think about it. Huh? We will come back to this tomorrow. I'll show you another example where you can actually see the X-ray emission. But in some high redshift radio galaxies and high redshift quasars, you can actually see X-ray emission from the lobes. Right? And I'll give you a hint, the physical phenomenon is not synchrotron, which it is for the lobes themselves. Right. So quasars actually show radio emission, which is very, very reminiscent of radio galaxies. Many radio loud quasars have features like this. And this was the starting point of what is called as the unification theory, wherein you try to have a simple model that unifies all these different classes of AGN. We'll come to that maybe in a couple of lectures. We'll start talking about the unification theory. But here I'd just like you to remember that in the radio loud quasars do show extended structures in many cases. In some cases they don't, but there are many examples where they do. And this is the core emission in the radio. This is what is referred to as the radio jet. And this one and this one is referred to as the radio lobe. So this is one radio lobe and this is another radio lobe. And this part is referred to as a hotspot. We'll revise that once again when we talk of radio galaxies. One thing that distinguishes quasars from radio galaxies is that most quasars show what are called one-sided jets. So you can clearly see the jet on this side, but you cannot see the jet on that side. So either the jet doesn't exist or it's missing, okay, or it's too faint to see, right? So there is some thing that you need to explain. We'll talk about that again when we talk of unification models.
Hello, sir.
Yeah.
Sir, that jet that you said is not seen. Is it not seen in any wavelength or just in this radio wavelength? These are all of this structure that you see in this image is purely seen in the radio. If you go and look at it in the optical, you'll detect this, a blue object over here. If you look at this same thing in the X-ray, you'll detect some X-ray emission here, except if it is at high redshift, when you will detect X-ray emission not from the jets. So you won't detect the jets in the X-ray, but you will detect the lobes in the X-ray if it is a very luminous radio galaxy or quasar at high redshift. That high redshift is important. By high redshift, I mean redshift greater than 1, let's say. Yeah, but so you won't see it. You won't see any of this structure in the radio. And therefore, when we talk of radio emission from AGN, that phenomenology and that the whole concept of radio galaxies and so on is peculiar to radio. Okay, it's not seen. Such kind of large extended structures are not seen in the other bands. Now, in some cases, the radio galaxies can be very large. So the end-to-end distance can be a megaparsec or even more, 2 megaparsec, right? Now, what does that tell you about the lifetime of the AGN phenomenon at the center?
So suppose, let us say this distance is, let's say this distance is 1 megaparsec. Okay, assume it's not in this case, but assume it is. What can you say about the lifetime of, what constraints can you put on the lifetime of the quasar phenomenon?
Hello, sir.
Yeah.
Sir, if we consider that the jets are moving like nearly light speed,
Yes.
and so if they switch off before reaching the end, then there should be a detachment from the origin, from the quasar, which should be seen.
Correct. Correct. Or they won't even form the lobes, because only
Yeah.
when they transport energy to the, from here, remember the energy is coming from here.
Yes.
These guys are passive objects. They are not producing any energy. The energy is coming from that accretion disk around the black hole. So energy is being transported from the center of the quasar to these lobes, right? And if the lobe is 1 megaparsec away, which means of 3 million light years away, then this has to last a minimum of 3 million years in order to power this. So the quasar lifetime cannot be less than 10 raised to 6 years. The quasar phenomenon, if it starts, probably lasts. Now there are other constraints. So these are very weak constraints, which tell us that the quasar phenomenon will last from somewhere between, say, 10 raised to 8 to 10 raised to 8.5 years. Very long lived. Okay. Before we go on, just a little reminder that the word quasar is used in sort of many different ways. So sometimes quasars without any extended structure are called quasars. Sometimes quasars with extended structure are also called quasars. Quasars without any radio emission at all are sometimes called QSOs or quasi-stellar objects, but sometimes they are also called quasars. So whenever you read a paper, you must be really careful in seeing whether these are radio dominated objects or not. And this is particularly important because as we shall again see in one of the later things, we now have a better theoretical understanding of what happens. And we believe that there are two modes in which a quasar or any AGN operates. One mode is when they are radiatively efficient, which is called as the quasar mode. And there is a second mode, which is radiatively inefficient, which is known as the radio mode. So whether there is radio emission seen from AGN or not tells you a lot about the mode of accretion that is going on around the black hole in that AGN. So we'll of course come back to that in greater detail in one of the later lectures.
Sir?
Yeah.
Is there a difference between radio quiet quasar and QSO?
Again, that is used interchangeably. Okay, there are some people who use radio quiet when there is a radio detection, but it is below 10 raised to 25 watts per hertz or R less than 1 and so on. But there are others who use it as, if there is no radio detection, they call it radio quiet, right? So it's a mess actually. You just have to be very careful. Usually in the paper that you're reading, they will carefully define of what they mean when they say radio loud, radio quiet, and so on. Okay. Now we move on to, so we have spent about two and a half lectures talking about quasars in detail. And I told you at the beginning that there was a reason that once I cover quasars in details, I'm going to cover the other categories fairly rapidly. I don't have to go into their details because many of their details are very similar to what we have studied in quasars. So we will only look at the major differences or the major properties of these other classes of AGN. Seifert 1 AGN, we have encountered these before when we were talking of the history of AGN. Carl Seifert studied them systematically in a paper in 1943. He found that they're almost always hosted by spiral galaxies in the nearby universe. They may or may not have radio emission. By nearby universe, one generally means redshift less than 0.1. The Seifert 1 AGN may or may not have strong radio emission. Their spectrum shows UV excess and strong broad and narrow emission lines, just like quasars. So in that respect, Seifert 1 AGN are just like quasars. However, this is a picture. Unlike to get the host galaxy images of quasars, we saw that one had to use the Hubble Space Telescope. For Seiferts, you don't have to. And there are two reasons for them. Seiferts are generally found only detectable only at low redshifts. And two, they are much, much less luminous compared to quasars. So quasars we saw dominate the light of the galaxy. They're much brighter than the galaxy itself. Seifert ones, on the other hand, although being quite bright, do not drown out the light of the galaxy. So you see two objects here, NGC 5548, which is a Seifert galaxy, and you can see actually diffraction spikes from the very, very bright nucleus that is there. But it's a nearby galaxy, so large angular extent, the point spread function is small enough that it doesn't drown out the rest of the galaxy. This is another spiral galaxy, except that this one doesn't have AGN, it's a normal galaxy, and therefore you don't see those diffraction spikes. So for the bright Seifert ones, you can, even an optical image like this will tell you that yes, there is an AGN at the center. Then of course you will have to take a spectrum in order to confirm its nature. Here is the full broadband SED of one of the Seiferts, NGC 3783. And you can see that at frequencies above 10 raised to 12 hertz, okay, which means in the sort of in the infrared and optical bands, they are much brighter than normal galaxies, which sort of look like this. This particular galaxy, do you think is going to be radio loud or radio quiet? It's going to be radio quiet, because see, the radio flux is 6 magnitudes, or this is a log scale, 10 raised to 6 times fainter than what it is, right? If it were a radio loud AGN, it would not fall off so precipitously. What does their spectrum look like? So we looked at the composite spectrum of quasars. Okay, this is what we had looked at earlier. And here you see the composite spectrum of many, many Seiferts, again obtained from the SDSS. And you see broad emission lines like this one. Any idea what this line might be? Look at this. Okay, it is the Mg2 line, magnesium 2 emission line. This one is the H alpha line, right? So you see, just like quasars, you see a blue continuum, and you see both broad and narrow emission lines in the spectrum. So they're clearly related to quasars, but if you take the total optical magnitude or luminosity, it will be much fainter than quasars. How much fainter? Say 100 times fainter, 10 times fainter, 50 times fainter than quasars. Otherwise, there isn't much of a difference. This particular composite spectrum doesn't go to very short wavelengths. Why is that? This is constructed from the SDSS and this is also constructed from the SDSS. But I was not able to go to shorter wavelengths than this. The reason for that is simple. There are a very large number of high redshift quasars, right? So for high redshift quasars, all these UV lines like the 1216 Lyman alpha line redshifts into the optical band where SDSS can take a spectrum of. But for Seyfert galaxies, which are relatively nearby, again, this is a selection bias. It's not that there are no Seyfert galaxies at high redshift, but Seyfert galaxies become too faint for us to detect them at high redshifts. And since you can't find them at high redshift, you only find them at low redshift, you'll never be able to observe the Lyman alpha line for a Seyfert galaxy without actually having a ultraviolet spectrograph. Okay. Right. Now, we looked at how one can find quasars, right? We use the UV excess and then look for new quasars. But if you were to find new Seyfert 1 galaxies, how would you go about doing that? Do you expect to see a blue nucleus at the center? Yeah? Yes or no?
Yes, sir.
Yeah, you would expect to see a blue nucleus. So for nearby Seyfert galaxies, you would be able to find them. And this is how Seyferts were first imaged. And they said, okay, this is a technique that Carl Seyfert used, that he took a lot of images of galaxies, found galaxies that are relatively faint which have a very bright blue nucleus, and then went and got a spectrum for them. But now that has been exhausted. Nowadays, we don't find Seyfert galaxies this way. We just go and get a spectrum of every galaxy there is, right? In surveys, large spectroscopic surveys like the Sloan survey. And some of them, a very small fraction of them, typically 1% or so, will turn out to be Seyfert galaxies. We've been saying Seyfert 1, and that is because there is, like Seyfert 1, there is a Seyfert 2. They're very similar, nearly identical in their properties to Seyfert 1s, except that they lack broad emission lines in their spectrum, right? The flux in the narrow line does not change with time. The broad line fluxes seem to change in Seyfert 2s and Seyfert 1s, but the narrow line fluxes that you see in the narrow lines of the Seyfert 2s do not seem to change with time. Again, this is an important observation which will be useful to us when we look at the unification theory. Okay, so one last topic which we will start discussing and take up in detail in the next class. This is about emission lines from AGN or from non-AGN sources. So can a normal galaxy show emission lines in their spectrum? We know that normally stars show absorption lines. So if you add up the spectrum of many stars, you'll have many absorption lines getting added together, giving you lots of absorption lines in the galaxy spectrum. But can there be a galaxy which shows emission lines?
Star forming regions in about emission lines.
Yes, that's exactly right. Star forming regions, which we refer to as H2 regions because they contain ionized hydrogen, those can produce emission lines in their spectrum, right? Now, remember, we are taking a spectrum only of the central region of the galaxies, because when we go looking for AGN, we know they're at the center. So we take a spectrum of the center. Could you have emission lines coming from the center? which are not from an AGN? Answer is yes. If you have a lot of gas that has fallen towards the central regions, and there is a lot of active star formation that's happening in the central region, you will have ionized hydrogen there, and you will see emission lines. So the question is there a difference in the ionizing spectrum of massive stars and that of AGN?
Hello, sir.
Yeah, go ahead.
Sir, the ionizing spectrum of a massive star will show emission mostly in the H alpha and
Yes.
near to that, while in AGN the emission will be in most likely in every wavelength.
Correct. That is right. So you will see optical emission, because what typically happens is massive stars typically produce a lot of UV photons. These UV photons ionize the gas in the H2 regions, and when the gas recombines to form again hydrogen, at that time the H2 photon gets emitted, right? It falls from the excited state to the Lyman state or to the Balmer level, n equal to 2. So yes, so what is the difference? Massive stars have a clear cutoff in their ionizing spectrum, because at the Lyman limit of helium, which is about 228 angstroms, helium, of course, like hydrogen, helium is there in reasonable amounts in the universe. So helium can also absorb, right? But anything beyond the Lyman limit of helium will find very, very difficult to travel to us. And therefore, the ionizing spectrum gets truncated at the Lyman limit of helium, even from the most massive stars, O-type stars. But the non-thermal radiation, which comes from AGN, extends to very, very, very much higher photon energies. As a consequence, the ratio of collisionally excited lines to that of lines which are produced in the course of recombination, which means in H2 regions, is larger in the case of AGN-like ionization radiation field. So if the radiation field is, the source of the radiation field is the AGN rather than massive stars, you do expect to see a higher ratio of collisionally excited lines with respect to the recombination lines. And that allows us to actually distinguish between star-forming galaxies at the center and AGN, right? So we'll start with that. I'll stop now. If there are any questions, I'll take them. Otherwise, we'll start with this again in the next lecture.
Sir?
Yeah.
So do these lines are same broad as in case of AGN?
Sorry?
So do these lines are same as broad as in case of AGNs?
They are the same lines, okay, but between AGN. So for example, you had the H alpha line in AGN, you'll have the H alpha line in star forming regions also. You had the O3 line in AGN, right? You will have the O3 line in star forming regions also. The only thing that will be different is the ratio of the strengths of these lines. That will be different. And you can use that, the ratio of the equivalent weights or the line strengths of these lines to distinguish between a spectrum of an AGN and a spectrum of a star forming region at the center of the galaxy. Okay. So is Friday a holiday by any chance?
Yes, sir.
It is, but if it's okay with everyone, I would like to have a class on Friday. Is it okay for everyone?
Yes, sir. I am okay with that.
Yes.
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 So if
Yes, sir.
yeah, so if people are okay, I would like to take a class because I'm going to have I have a conference to attend in early June. So I'm trying very hard to sort of finish the lectures by that time, before the second week of June. So we will have a class on Friday at the same time, and then we'll continue this discussion on the distinguishing AGN from star formation and so on. Okay. So I have, by the way, added recordings of all the first 3 or 4 lectures on the website. The video recordings are there, in addition to the slides themselves. So even today's thing has been recorded and will be added there. So if anybody misses a class or one of your friends misses a class, just tell them to look at the recordings. Okay, so I think I'm going to end the class now. And I'll see you all on Friday.